Internet security is a high priority these days, and one of the methods, algebraic crypto systems, is based on general polynomial functions. Hi, my name is Tom Atwater, and that's what we'll be exploring today. Let's start by discussing the conjugate zeros theorem. Conjugate zeros theorem says if p of x defines a polynomial function having only real coefficients, and if a plus bi is a zero of px, then the conjugate a minus bi is also a zero of p of x. Let's do an example. Find a cubic polynomial function p in standard form with real coefficients having zeros of 3 and 2 plus I. Okay, well, what that means is we're going to be looking for a polynomial of degree 3 that has zeros 3 and 2 plus I. Now, by the conjugate zero theorem, if 2 plus I is a 0, then 2 minus I must be a 0 as well. So the factors of this polynomial will be x minus 3, x minus parentheses 2 minus I, and then x minus parentheses 2 plus I. So again, by the conjugate zeros theorem, we know that if we have 2 minus I, we have to have 2 plus I. So we need to multiply this out and simplify it to put it into standard form. Let me deal with these two first. So we'll write our x minus 3 and leave it in its parentheses as such. Now what I'll do is distribute the minus signs, and that's going to give me x minus 2 plus I, x minus 2 minus I. I want you to notice now, I'm going to do a little bit of grouping here. I'm going to have my x minus 3, and now notice that I can put x minus 2 in parentheses and then plus I. And I'm going to do the same thing here, put x minus 2 in parentheses minus I. And I'm doing that because I'm hoping that it's now clearer for us to see that this is just the difference of two squares, x minus 2 plus I and x minus 2 minus I. And the reason that that's nice for us is that it simplifies into x minus 2 squared, like this, and minus I squared. The middle terms drop out because of the difference of two squares. So now what we have is x minus 3, and then we have to expand this. It becomes x squared minus 4x plus 4. And then remember that I squared is negative 1, so minus a negative 1 is plus 1. All right, so now we have x minus 3 times x squared minus 4x plus 5. We distribute from this to here, and let's do the x first, and we get x cubed minus 4x squared plus 5x. Next, do the negative 3, and we get negative 3x squared. Then negative times a negative for plus 12x, and then negative times positive gives me negative 15. Let's combine like terms. There's no other cube term. We have minus 4x squared and minus 3x squared for minus 7x squared. We have 5x and 12x for plus 17x. And then finally, the constant term of minus 15. So the cubic we're looking for is x cubed minus 7x squared plus 17x minus 15. Well, now it's time for you to try a problem. Here's the example that I would like you to do. Find a polynomial function p of x of the least degree possible having real coefficients with the following zeros: 3 plus 2i, negative 1, and 2. Pause the video to work on this problem. When you are finished, restart the video to check your solution. Let's find out how you did on that problem. Now remember, I gave you 3 plus 2i as a 0, and by the conjugate zeros theorem, that means 3 minus 2i is also a 0. So the factors we have, remember -1 and 2 were both zeros, so that means this. The factors that we have for this polynomial equation are x plus 1, x minus 2, x minus 3 plus 2i, and x minus 3 minus 2i. Alrighty, so now I'm going to leave these two as is for the moment and deal with these two in the same manner that I did before. That is, distribute the minus sign, so I get x minus 3 minus 2i, and I get x minus 3 plus 2i. Leaving these as is, then noticing once again that I can take those and group them so that we can see once again we have the difference of two squares, which means that this is x minus 3 squared minus 4i squared. We can expand out this, leaving these two the same. So this would be x squared minus 6x plus 9. I squared, remember, is -1, so this becomes positive 4. So we have x plus 1 times x minus 2 times x squared minus 6x plus 13. I need to now distribute into here. So what I'm going to have is x plus 1, and now distribute the x, and we get x cubed minus 6x squared plus 13x. Now distribute the minus 2, and we get minus 2x squared plus 12x minus 26. We can simplify inside there a little bit because we have some like terms. So let's take x plus 1 times x cubed minus 8x squared. Then we have plus 13 plus 12x for plus 25x, and then the constant minus 26. We need to distribute the x to each term, and so we get x to the 4th minus 8x cubed plus 25x squared minus 26x. Now we need to distribute the positive 1, so we get plus x cubed minus 8x squared plus 25x minus 26. And finally, we can combine terms. There's no combine like terms. There's no other x to the 4th. We have negative 8x cubed. We have a positive x cubed, so that's minus 7x cubed. 25x squared and negative 8x squared leaves me with 17x squared. Then we have minus 26x plus 25x for minus x, and then the constant term, negative 26. So that is the polynomial of least degree that has the zeros of 3 plus 2i, 3 minus 2i, -1, and positive 2. X to the 4th minus 7x cubed plus 17x squared minus x minus 26. Now we'll extend this idea by examining the fundamental theorem of algebra, which says every function defined by a polynomial of degree 1 or more has at least one complex zero. Okay, now the fundamental theorem of algebra mathematically leads into something called the number of zeros theorem. So let's take a look at that. It says that a function defined by a polynomial of degree n has at most n distinct complex zeros. It'll be helpful to look at an example. So let's look at find all the zeros of p of x equals x to the fourth minus 7x cubed plus 18x squared minus 22x plus 12, given that 1 minus I is a 0. Well, if we know that 1 minus I is a 0, then we also know that 1 plus I is a 0. So let's take a look at those two factors to begin. That we have x minus 1 plus I, and we have x minus 1 minus I. Once again, let's distribute the minus sign. And notice that we have set up for us the difference of two squares. So it's x minus 1 squared minus I squared. That gives us x squared minus 2x plus 1. And then remember, I squared is negative 1. We're going to subtract negative 1, which means we have to add it. So we have x squared minus 2x plus 2. And that tells us we can use this to do a long division problem and divide that into our original polynomial. So let's set that up. We have x squared minus 2x plus 2, and we're going to divide that into x to the fourth minus 7x cubed plus 18x squared minus 22x plus 12. Okay, so we look at this term, it goes in x squared times. So we put x squared up here, multiply this out, we get x to the fourth minus 2x cubed plus 2x squared. We subtract this off, and of course the x to the fourths cancel. This is negative 7 plus 2x, so that's negative 5x cubed. This is 18 minus 2 for 16x squared. Let me bring down the negative 22x. And now we look at taking x squared into negative 5x cubed. Negative 5x cubed is divided by x squared, leaves us with negative 5x. So we have negative 5x cubed, then negative 5x times negative 2x is a positive 10x squared, and then 2 times negative 5x is a negative 10x. So now we need to subtract that off. So let's put parentheses around it, the minus sign. Of course, when we subtract, that means the x cubes cancel out. 16x squared minus 10x squared gives me 6x squared. Negative 22x plus 10x is negative 12x. And then bring down the plus 12. So now x squared goes into 6x squared 6 times. And that's going to give me 6x squared minus 12x plus 12. So that when I subtract that off, it's going to be 0. What that tells me then is that x squared minus 5x plus 6 is another expression which is part of this polynomial. So let's take that, factor it, and find 2 more zeros from this quadratic. So let's take x squared minus 5x plus 6 and set it equal to 0. Then that'll give me x minus 3, x minus 2 equals 0. So that gives me x equals 3 and x equals 2. So my solution set for this quadratic are the numbers 2, 3, 1 plus I, and 1 minus I. All right, great. So that was a very good example of where we used the rational zeros theorem and the conjugate zeros theorem to find the solutions. Okay, the next thing I'd like to look at with you is another theorem called the rational zeros theorem. The rational zeros theorem, let P of x equal the polynomial a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub 1 times x plus a sub 0, where a sub n does not equal 0. And that defines a polynomial function with integer coefficients. And if p divided by q is a rational number written in lowest terms, and if p divided by q is a 0 of p of x, then p is a factor of the constant term a sub 0, and q is a factor of the leading coefficient a sub n. Now that was a lot of words with a lot of math, and I think the easiest way to really explain that is to do an example. So let's take a look at an example. Perform the following for the polynomial function defined by p of x equals 6x to the fourth plus 7x cubed minus 12x squared minus 3x plus 2. List all the possible zeros. Use a graph to eliminate some of the possible zeros and find all the rational zeros and factor p of x. Okay, so what we know from the rational zeros theorem is that p is going to be a factor of 2. And that q is a factor of 6, which means p divided by q takes on the following possibilities. We have plus or minus 1, plus or minus 2, plus or minus, and of course I'm getting these because I'm taking the 2 and all of its factors, which are 1 and 2, and then the factors of 6, which are 1, 2, 3, and 6, and I'm dividing those. So I get this because of the 1 divided by the 1, and of course the 2 divided by the 1. Then I have plus or minus a half by 1 divided by 2. The 2 divided by 2 just gives me this result. So then I have plus or minus the 1 divided by 3. I also have plus or minus the 2 divided by 3. And then when I take the 1 divided by 6, I get plus or minus 1/6. And then finally, the 2 divided by 6 just repeats the plus or minus 1/3. So here are all the possible zeros of the function. Now, what we're going to do is we're going to turn to the graphing calculator, and we're going to graph this polynomial because it'll help us to eliminate some of these possibilities. Okay, so here we have our keystrokes on the right-hand side that we need to enter to graph this equation. So we start off by hitting the y equals or the equation key, clearing out anything that's there. Type in 6 times x raised to the 4th power plus 7x, and then we can hit the math button and selection number 3, which is the cubes for 7x cubed, minus then 12, so 1, 2, x, and then squared button, minus 3, the x key, then plus 2 as the constant. And now we can graph it. Now this is a quartic equation, and what we're going to notice is that over here on the left-hand side of the graph, we can say that there are no zeros less than -2. And we can say that there are no zeros greater than 1. In addition, we know that -1 is not going to be a solution because the graph does not cross the x-axis at -1. So to find out for sure if both 1 and -2 are in fact zeros, we'll use the remainder theorem along with synthetic division. So what we have is we're going to divide by 1, and the coefficients of our polynomial are 6, 7, -12, -3, and +2. So for synthetic division, we bring down the 6, multiply times the 1, add these together for 13. Repeat the process, 1 times 13, add them together for 1. Repeat the process, 1 times 1 for 1, add them together for -2. Repeat the process, -2 adds up to 0. The fact that that term is a 0 tells us that 1 is in fact a root of this polynomial. Now, let's check out to see that -2 is a root. And what we can do here is use the coefficients here and divide synthetically by the -2, because if -2 is a root of this, then it's certainly a root of the original one. So we bring down the 6, multiply -2 times 6 for -12, add them together for 1. -2 times 1 is -2, add them together for -1. -2 times -1 is +2, add them together, and we get 0, which tells us that -2 is also a root. In addition, what it tells us is we have the polynomial 6x squared plus x minus 1 left over, and what we should do is see if we can factor this, or in some way figure out the quadratic, what the two zeros of this are. So let's pull that up to here and work that out. We have 6x squared plus plus x minus 1 equaling 0. And we look to factor this, and what we know is if we do 3x and 2x, of course that's 1 and 1 in order to get 1 here. So the only question is which one is positive and negative, and of course this needs to be positive, this needs to be negative, so that we end up with a positive x in the middle. Now we know that 3x minus 1 equals 0, 2x plus 1 equals 0, and that tells me that x is equal to 1/3 and x is equal to -1/2. So the four zeros for this polynomial are -1, or actually let's start and put them in order, -2, comma, -1/2, comma, 1/3, and 1. And those are the four zeros of our polynomial. Using the graphing calculator eliminated some of the work for us. Now there's another theorem that will aid us in finding the real zeros of a function, and it's called Descartes' rule of signs. And it tells us, let p of x define a polynomial function with real coefficients and a non-zero constant term with descending powers of x. The number of positive real zeros of p either equals the number of variations in sign occurring in the coefficients of p of x, or is less than that number of variations by a positive even integer. Part B, the number of negative real zeros of p either equals the number of variations in sign occurring in the coefficients of p of -x, or is less than that number of variations by a positive even integer. Let's do an example of Descartes' rule of signs. Determine the possible number of positive real zeros and negative real zeros of the polynomial p of x equals x to the 4th minus 6x cubed plus 8x squared plus 2x minus 1. So if we use Descartes' rule, we want to look at p of x itself. And what we'll notice is that there are 3 sign changes there. We go from x to the 4th, which is positive, to negative 6x cubed, so that's 1. Then we go back to a positive number, that's 2 changes. The next coefficient 2 is positive, but then the constant term is negative. So we have 3 changes there. What that tells us then is that we either have 3 or 1 real positive 0. Remember, because it's either equal to the number of sign changes or it's equal to a even number, in this case 2, less than that, so 1. Now, let's look at p of negative x. P of negative x, we have to replace all x's with negative x. So that's negative x to the 4th. Then we're going to have minus 6 negative x cubed. Then we're going to have plus 8 negative x squared. Then we're going to have plus 2 times negative x, and then minus 1. We have to simplify that a little bit in order to be able to tell what the coefficients are going to be. But negative x to the 4th is just x to the 4th. Negative x cubed remains negative, but then we have a negative 6 in front of it, so that becomes positive 6x cubed. Negative x squared, of course, is positive, and it remains positive with the positive 8x squared. 2 times negative x gives me negative 2x and then minus 1. So when we look at this problem in terms of the sign changes, we have positive, 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 then it changes. It goes to negative. It stays negative, which means there's 1 sign change. So that means that it has 1 negative real 0. Okay, so that's an example of using Descartes' rule of signs to help determine how many positive and how many negative real zeros there are. Well, we have one more theorem that will help us in determining zeros called the Boundedness Theorem. And it says, let p of x define a polynomial function of degree n greater than or equal to 1 with real coefficients and with a positive leading coefficient. If p of x is divided by, synthetically, by x minus c, and part A, c is greater than 0, and all numbers in the bottom row of the synthetic division are non-negative, then p of x has no 0 greater than c. Part B says that if c is negative, and all numbers in the bottom row of the synthetic division alternate in sign, with 0 considered positive or negative as needed, then p of x has no 0 less than c. Again, I think the easiest thing is to do an example. So we have showed that the real zeros of the polynomial p of x equals 2x to the 4th minus 5x cubed plus 3x plus 1 satisfy the following conditions. A, no real 0 greater than 3. B, no real 0 less than negative 1. So, to use the boundedness theorem, we will do a synthetic division by 3. And let me write that down on the board, where we write down the synthetic division by 3 using the polynomial p of x equals 2x to the 4th, so we have coefficient of 2. Coefficient of x cubed is minus 5. And then we have plus, there's no x squared coefficient, and then we have 3 for the coefficient of the linear term, and then plus 1. Okay, so now we bring down the 2, multiply 3 times 2, which gives us 6, add these together for 1, repeat that process, 1 times 3 for 3, add them together for 3, 3 times 3 is 9, add them together for 12, 3 times 12 is 36, add those together for 37. And what we see is that all of these are non-negative. And what that tells us then is no real zero greater than 3. Well, we can repeat that process for negative 1. For negative 1, we have the same coefficients, 2, negative 5, 0, 3, and 1. We bring down the 2, multiply -1 times 2 for -2, add them together, -7. -1 times -7 is +7, which we add to 0 for 7. And then -1 times 7 is -7, add that to 3 for -4. And then -1 times -4 is +4, which gives me 5 when I add it to the 1. So here, we'll see that there is alternating signs, positive, negative, positive, negative, positive, and that then tells us that no real zero, that this original polynomial has no real zero less than -1. All right, that was great. In this lesson, we explored the theory of polynomial functions. Be sure to work the exercises that your teacher assigns, and we'll see you next time.